Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Hidayah Ghazali from UMT GAMBANG PAHANG. I'm from Faculty Industry Science and Technology. My co-inventor in this research are Dr. RODZIAH binti NAZLAN and SITI NORAIN binti ABDUL. My topic for this research is waste to wealth, from printer toner waste into valuable magnetic materials. The outline in this presentation, firstly is introduction, second objective, methodology, results and discussion, and lastly is conclusion. Next is introduction. So, the most flexible soft magnetic material which commercially used in high power devices and high frequency application is ferromagnetic material, or known as ferrites. Ferrites are ceramic materials consist of iron as its main constituent and generally hard, brittle, iron containing and polycrystalline. There are two types of ferrite, which are soft and hard ferrite. As you can see in this figure, soft ferrite have low coercive force, which means that it has low coercivity and easy to magnetize and demagnetize. While for hard ferrite material, it has large coercive force, which means that it has high coercivity and difficult to magnetize and demagnetize. Next is e-waste. The printer toner waste, which also a part of e-waste, also known as waste electrical and electronic equipment (WEEE). The total solid waste worldwide comprised of 5%, which is roughly about 40 million metric tons of e-waste production globally per year that ends up in landfills. The residual toner powder has 8% for an end-of-life toner for each cartridge that has been disposed. The waste toner composition in each toner cartridge are iron oxide, carbon black, resins, charge control agents, and imaging materials. Next is waste toner problem. The toner waste was a big threat to environment, especially to the human health, as the toxic chemicals leak out of the toner cartridge that contains dangerous composition, as I mentioned just now. It also have high toxicity if inhaled due to its fine particle size. Besides the particle size, it also combustible. So when the toner powder is airborne, the risk of dust explosion increase. This is why the recycling of waste toner was important, which not mainly focused on resource reutilization only, but also the environmental protection. Next is objective. First is to recover the magnetite Fe3O4 from waste toner by magnetic separation technique and convert into hematite Fe2O3 using reduction technique. Second is to synthesize nickel zinc ferrite using extracted iron oxide from waste toner powder. And lastly, to study the structural, microstructural, and magnetic properties of nickel zinc ferrite prepared using extracted Fe2O3 iron oxide as main component. Next is methodology. First is sample preparation. Next is sample characterization, which involve XRD and SEM-EDX instrument. And then magnetic separation process, which involve waste toner powder and ethanol solution. Next is centrifuge process, where the time involved is 10 minutes at 500 RPM at 27 degrees Celsius. For grinding process, the sample involved is PET waste plastic and the time is 1 minute. Next, for pellet sample fabrication, the time used is 10 minutes and the pressure is 3 tons. After that, for reduction process, the powder and pellet was formed and the temperature used were 500 degrees Celsius and 1400 degrees Celsius. The holding time is 2 hours and the heating rate for each sample was 4 degrees Celsius per minute. And lastly, the sample will be characterized using SLD, SEMEDX, and VSM instruments. Next, for flow procedure, first figure is the waste toner was collected from the toner cartridge, and then the waste toner was mixed with ethanol, and next, the iron oxide was extracted using magnet bar. The fourth figure, the collected iron oxide was dried in an oven to evaporate the ethanol. And then the iron oxide was centrifuged for 10 minutes and dried in an oven for 4 days. For the sixth figures, the iron oxide becomes sludge, which had soft and rubbery texture. The magnetite powder, after being sintered at 500 degrees at 7th picture. Next is the magnetite powder pellet was formed. The magnetite and pellet was mixed with PET to be sintered at 1400 degrees. After that, the hematite powder formed after being sintered. And lastly, the nickel zinc ferrite powder was formed after being sintered. Both hematite and nickel zinc ferrite powder were sintered at 1400 degrees Celsius. Next is formation of nickel zinc ferrite. First is magnetite purification, where the magnetite is undergoing sintering process at 500 degrees Celsius. And then reduction process for magnetite conversion into hematite, where the magnetite added with PET waste plastic to form hematite and that was sintered at 1400 degrees Celsius. The conversion of magnetite to hematite due to an oxygen loss from magnetite at high temperature. And then nickel zinc ferrite preparation. Hematite will be added with nickel oxide and zinc oxide to form nickel zinc ferrite and sintered at 1400 degrees Celsius. Next is sample preparation. Firstly is the mixing of raw material, where iron oxide was added with nickel oxide and zinc oxide. After that, the pellet fabrication, where the binder used was polyvinyl alcohol PVA and lubricant was zinc stearate. Next, for sintering process, powder and pellet form at specific time, temperature and heating rate. Next is sample characterization. The first instrument used was the Rigaku mini flat X-ray diffractometer, which to determine phase and particle size, where the two theta used was about a range of 20 degree to 80 degree. The second instrument used was Hitachi plus benchtop scanning electron microscope SEM with EDX, where it was to observe microstructure, and EDX used to identify the elemental and quantitative compositional information. Next is Lakeshore vibrating sample magnetometer, which to determine saturation magnetization, MS, coercivity, and squareness. After that, results and discussion. For structural and microstructural analysis, the sample used for SLD were waste toner, magnetite, hematite, and nickel zinc ferrite. For SEM-EDS, the sample used was waste toner and hematite. For magnetic analysis, the sample used for VSM instrument were magnetite, hematite, and nickel zinc ferrite only. For SLD analysis, first, the phase identification of sample were determined. As you can see in this table, for waste toner sample, the highest percentage was magnetite. For magnetite, For magnetite sample, the highest percentage also hematite. And then for hematite sample, it has highest percentage of carbon, C60, which is 88% due to addition of PET. And lastly, for nickel zinc ferrite, the highest percentage was nickel oxide. As you can see in this SRD spectra, for magnetite sample, the hematite was already formed even though it was sintered at 500 degrees Celsius. After that, the SRD parameter for each sample were determined such as HKL, heat position, D spacing, FWHM, phase group, and lattice constant. Next, for SEM EDX analysis, first is SEM image of waste toner at 300 magnification, 1000 magnification, and 3000 magnification. Second is SEM image of hematite at 300 magnification, 1000 magnification, and 3000 magnification. Both of the sample were observed in same magnification. As you can see in C figure for SEM image of waste toner, it has merely spherical shaped particles, and after being sintered at 1400 degrees Celsius, the particle became a flake shape with a larger particle size, as you can see in C figure for SEM image of hematite. Next is graph of particle size distribution for toner waste and hematite. As you can see in this graph distribution, the lowest grain size of toner waste sample was at a range of 41 to 60 micrometer, and the highest was at 1:1 to 140 micrometer. As for hematite sample, the highest particle size lays at the range of 81 to 120 micrometer. Next, for EDX analysis, for waste toner sample, the element exists in waste toner sample were carbon, oxygen, iron, where the image width was 175.7 micrometer. As for hematite sample, the highest percentage was oxygen with 53.91%, which the image width of hematite sample was 117.1 micrometer. Next is BSM analysis. The magnetic parameter of extracted magnetite, hematite, and nickel zinc ferrite were saturation magnetization, retentivity, coercivity, and squareness. The saturation magnetization of magnetite is the highest because no addition of PET as reducing agent. If there is no addition of PET, the saturation magnetization of hematite and nickel zinc ferrite will be much higher because PET not contributing much to magnetization of sample but only act as reducing agent of the magnetite to hematite. The squareness of the nickel zinc ferrite showed the highest value, which indicates that nickel zinc ferrite is suitable to be used for data storage in computer such as CD, RAM, and ROM. Next, the graph of magnetization versus magnetic field was plotted as shown in this slide. According to the graph plotted, the area for all sample had small area of hysteresis loop. The characterized sample was soft ferrite due to small loop area and smaller cohesive force. Smaller hysteresis loop shows smaller hysteresis loss. Hence, smaller cohesive force indicates that the sample is easier to magnetize and demagnetize as compared to samples with having larger cohesive force. Lastly is conclusion. Based on SRD analysis, the major composition in waste toner sample was iron oxide. After the sintering process at 500 degrees Celsius, the iron oxide became magnetite powder. The addition of PET to magnetite powder acts as reducing agent for reduction process from magnetite to hematite. As for saturation magnetization, magnetite sample has the highest MS with 3.4878 EMU per J. Area for all samples have smaller cohesive force, which means that they have smaller hysteresis loss. Hence, the samples were easily magnetized and demagnetized. Lastly, for squareness ratio, nickel zinc ferrite had larger value with 0.45722 compared to magnetite and hematite sample which indicates that it is suitable to use in data storage application. That is all from me. Thank you.